Welcome to The Explainer. Look, if you're tuning in, chances are you've recently been handed a water quality lab report or maybe a soil analysis, and you immediately felt that familiar wave of complete and utter overwhelm. You know the feeling, right? Staring at a dense spreadsheet packed with acronyms, decimal points, and scientific jargon. It's supposed to give you answers about your water or industrial stream, but instead, it just leaves you with a headache. Well, you are not alone. Today, we're going to break down exactly what those numbers actually mean, and more importantly, what they might be hiding. Okay, let's dive into this. When you get an ICP test result, it is so tempting to look at it as an absolute answer key. You see a number, you assume that's the exact reality of your sample. Boom, done. But what if I told you that a lab report isn't an answer key at all? Actually, scratch that. It's more like a mystery case file. It's a collection of clues that desperately needs decoding. See, a single number doesn't tell the whole story. It just tells you how the instrument reacted to your sample under a very specific set of conditions. Our job today is to learn how to read between those lines. To decode these clues, here is our investigator's checklist. We're going to cover the ICP mystery, decoding the units, the zero illusion, matrix effects and limits, and finally, common testing pitfalls. Let's head straight to the scene of the crime with Section 1, the ICP mystery, decoding the case file. Before we can really solve this mystery, we have to understand our primary tool, ICP testing. ICP stands for inductively coupled plasma. Now, I know that sounds like a laser weapon from a sci-fi movie, but let's break down the jargon real quick. When a lab uses ICP, usually ICP-MS for mass spectrometry or ICP-OES for optical emission spectrometry, they are using highly advanced instruments to quantify metals and other elemental constituents in your sample. At a super high level, these machines use incredibly hot plasma to literally break your sample down into its basic atoms and ions so they can be counted. It's an absolutely phenomenal technology. But as you'll see, the counting process isn't always perfectly straightforward. This brings us to the illusion of precision. You might get a report that says you have exactly 4.327 parts per million of a certain metal. That highly specific number looks incredibly trustworthy, right? I mean, it's got 3 decimal places. But a single number is never the whole truth. Its true value depends entirely on how it was generated, the sample preparation, and the metrics running behind the scenes. Without that context, that precise little number might actually be leading you completely down the wrong path. And that brings us to Section 2, and our first major clue: decoding the units, weighing the evidence. And this brilliantly illustrates one of the most frequent traps people fall into. On your report, you'll commonly see units like mg per L, milligrams per liter for liquids, or mg per kilogram for solids. But right next to it, or maybe on a report from a totally different lab, you might see mucograms per L, micrograms per liter. Now, a microgram is 1,000 times smaller than a milligram. So if you compare a result of 5 mg per L to 500 mucograms per L without doing the mathematical conversion, you might panic, thinking the 500 is a massive spike, when in reality, the 500 microgram sample actually has a much lower concentration. You always have to weigh the evidence using the exact same scale. But units aren't the only mathematical hurdle here. As a data detective, you really have to look for hidden clues, and one of the absolute biggest is dilution. See, ICP instruments measure elements by comparing them to a calibration curve. But if your sample is too concentrated and falls way outside that curve, the lab has to dilute it to read it properly. The trick is, did the lab mathematically correct the final number back to the original concentration? Sometimes miscommunication happens, or redilution artifacts completely mask the original concentration. So always ask, is this reported number for the original sample or the diluted one? Okay, moving right along to Section 3, the zero illusion, hearing whispers in a crowd. We're about to tackle one of the biggest misconceptions in scientific testing. Values marked as not detected do not necessarily mean the element is absent. Look, if your report says ND or below detection limit, it is so incredibly easy to celebrate and say, awesome, there is 0 lead in this water. But that's false. Not detected simply means the element couldn't be reliably distinguished from the background noise of the instrument under that specific method sensitivity. Bottom line, it just means the instrument couldn't see it. It absolutely does not mean it's not there. And this is exactly why you need to pay close attention to data qualifiers. Some labs will give you a number, but they'll flag it with a letter, often a J-type qualifier. What this means is that the lab detected something, but the concentration is so dangerously close to the detection limit that they just can't be 100% confident in the exact number. It's an estimated concentration. If you're doing compliance checks, environmental assessments, or process troubleshooting, knowing that your number is a lower confidence estimate is literally just as crucial as the number itself. Let's keep following these clues right into Section 4, Matrix Effects and Limits, unpacking the interference. Let's see how the sample's own chemical makeup can actually distort the evidence. Remember how we just talked about the detection limit? Well, there isn't just one type of limit. Labs use different terms, and you really need to know the difference between MDL and LOQ. The method detection limit, or MDL, is the absolute lowest concentration that can be detected at all. The limit of quantitation, or LOQ, is the lowest concentration that can actually be measured with acceptable accuracy. Think of it like trying to hear a whisper in a crowded room. The MDL is the exact moment you realize someone is whispering. The LOQ is the moment you can actually understand the words they're saying. And because every room, or in this case every sample, has a different crowd size, these limits just aren't universal. They vary wildly based on sample size, instrument settings, and analysis conditions. To truly understand why those limits change, you've got to look at the journey of your sample. Step 1 is collection. Step 2 is digestion and filtration, often using some pretty strong acids. And step 3 is the actual ICP analysis. Now, I really want to emphasize step 2 here. What the machine measures is only the lab extractable fraction. So if your question is, hey, how much of this metal is in my soil, but the acid digestion step only dissolved half of that metal, well, the reported number isn't going to answer your true question. The prep steps heavily dictate the final number. And during all that prep and analysis, the sample's matrix gets in the way. The matrix is basically all the other stuff in your sample. The salts, the acidity, the organics, the particulates. These can introduce overlapping spectral lines, which is a fancy way of saying the machine confuses one element for another, or chemical interferences that suppress the signal entirely. If these matrix interferences aren't properly accounted for by the lab, they will absolutely create completely false readings. All right, we are in the home stretch now. Section 5, Common Testing Pitfalls, Solving the Case. Let's take everything we've learned and make sure we don't get tricked by the data. So the crucial point is you now have an actionable checklist to use the very next time you look at a lab reports. Do not compare units without doing the mathematical conversion. Do not ignore those tiny little letter qualifiers next to your numbers. Never forget to ask about dilution or sample mass corrections. Stop assuming that not detected equals an absolute 0. And please be incredibly careful about mixing different methods or comparing detection limits between two completely different laboratories. If you really want to find the true story, you've got to look beyond that basic results table. Empower yourself, ask the lab for their quality control documentation, ask for the method descriptions, the blank samples, the calibration checks, and their duplicates. Analyzing the context, how the samples were collected, prepped, and checked for quality. That is exactly what turns a simple, confusing table of concentrations into powerful, actionable evidence. Which leaves us with one final, vital question for you to consider the next time a dense spreadsheet lands on your desk. Are you just reading the numbers, or are you reading the whole story? Because now you actually have the tools to look past the illusion of precision and uncover the reality of your data. Thank you so much for joining me on this explainer. Stay curious and happy investigating.